Hello, so this is our last video covering the second half of chapter 10, which will mostly cover valence bond theory, our third theory that we're going to be talking about regarding chemical bonding. Before we get into valence bond theory, what I want to do though is tackle one more issue regarding VSEPR theory, which I didn't include in the last video. And that is applying VSEPR theory to large molecules where you have more than one central atom. So let's go ahead and put that on the board. So sometimes I've been calling it VSEPR theory, sometimes I call it VSEPR modeling. It's the same thing. So applying VSEPR theory to large. Now usually what gets us large molecules is the ability of carbon to form linkages with other carbons. So usually when we talk about large molecules, we're usually talking about organic molecules. So that's what I'm going to say here, large organic molecules, carbon-containing molecules. And the reason that this is heading all into itself is because a large molecule will not just have one central atom. So with, or let me say that don't have just one central atom. Because remember, that's how you tackle VSEPR theory. You locate the central atom and you count the number of electron groups around it. So what happens if you have more than one? So let's look at an example. Alrighty, so with these types of questions, I wouldn't necessarily be asking you to come up with the Lewis structures. The larger the molecule, the more you kind of have to know a little bit of the organic chemistry behind it to figure out the Lewis structure. So with this, I want you to just accept that this would be a Lewis structure that would be given to you, okay? So this is on your paper already. You don't have to figure this out yourself. But this is a molecule. And so if you were trying to figure out, okay, what's the shape of the molecule? What are the bond angles? Obviously, you can see that this is drawn like a Lewis structure where everything is just very grid-like. Lewis structure is not there to tell you the shape. It's just there to tell you where the single bonds are, the double bonds, the lone pairs, and that kind of thing. But if we want to apply VSEPR theory to it, we're asking a different question. What are those bond angles? And usually you would say, locate the central atom and count the number of electron groups around it. However, when you look at this, you might say, well, what's the central atom? Now, on one hand, some people might say nitrogen, because it's kind of seems to be in the middle, but like, what about what's going on over here? And so when you have a larger molecule where there's not just one central atom, what you want to do is you want to replace that word central with just interior. Any interior atom, okay, where you're not a terminal atom. So let's contrast terminal versus interior. Terminal means that's the last atom and there's no other atoms after it in terms of branching. So this is a terminal atom, terminal, terminal. But anytime you have an interior atom that has like two joints, you're going to have to analyze what shape is going around that atom, and that will end up dictating the turns that the molecule will take. So really what you want to do is you want to analyze any interior atom, and at that point you're going to have to ask the VSEPR modeling questions. So rather than just one central atom, you're going to analyze any interior atom. But after that, the topic is exactly the same. So let's go ahead and look at carbon. What's going around, what are these bond angles around carbon? So you're just going to literally fixate right around carbon and count the number of electron groups, 1, 2, 3, and get that number. From that number, you can answer so many questions here, okay? From that number, you can get the electron geometry. The electron geometry will just be the exact name that was in that table that we created. So that's going to be trigonal planar. I'm going to abbreviate a little bit here, trigonal planar. You can get the molecular geometry. Now, if they're all bonding groups, like they are here, none of them are lone pairs, it's going to be the exact same word, trigonal planar. The molecular geometry will be the exact same word. You can also get the bond angles, 120. And you can also get the hybridization, SP2. All of that comes from that number. So now let's ask the same question over here to the nitrogen. The nitrogen has how many pairs? 1, 2, 3, sorry, not pairs, but electron groups. 3 electron groups. So his electron geometry, once again, is also trigonal planar. Now, his molecular geometry, if one of the groups is a lone pair, the molecular geometry is not going to be the same as the electron geometry because there's no atom terminating at one of those, at the end of one of those electron groups. You can either use table 10.1 to locate the exact name. This is a name that we actually, you've already actually seen. If you think about it, what's going on at that nitrogen? If you just look at what's going on at that nitrogen, he's trigonal planar with his electron groups. One of them is a lone pair. The other 2 go down. So that molecular geometry, at least in this little segment of the molecule, you've seen this before. If it looks like that boomerang shape, it's called bent. So this one is also called bent when you've got trigonal planar electron geometry, but one of them is a lone pair. In terms of the bond angles, it's 120, but it's going to be less than 120 degrees because of the effect of that lone pair. I've just erased it, but remember the lone pair will deviate that angle slightly. And then the hybridization remains sp2. The hybridization is not going to change with the lone pair. On the oxygen, let's do the same thing. The oxygens, magic number is 1, 2, 3, 4. Make sure you always remember lone pairs count as electron groups in VSEPR theory because they take up room. They elbow their way around as well. Electron geometry would be tetrahedral. Molecular geometry is going to be bent. It's very similar to what's going on with water. When you have four electron groups, but 2 of them are lone pairs, the molecular geometry is just that bent shape. The angle, less than, because of the presence of 2 lone pairs, 109.5 degrees, and the hybridization sp3. So what I usually do is kind of organize everything that I can tell from those numbers of electron groups. But if someone was to ask you to take that information and draw a VSEPR model, okay, remember this here is the Lewis structure. If you were to be asked to draw a VSEPR model of this same molecule, the way that you would do it is this. Start with the first interior atom and just put it on your paper, carbon. And what you want to do is just fixate just on this section of the molecule, okay? Just almost pretend that it's just a small molecule for a minute. You've already analyzed that it was trigonal planar, and so just draw it as a trigonal planar. Now, sometimes, by the way, you can draw a trigonal planar like this, or you can draw a trigonal planar, if you think about it, like this. And I'm going to do it like that. They're both Y shapes. I'm going to do it like this. H going to, let me do the other H up here, and let me do the double bond to the end here. And once again, you need to have that bond angle labeled, 120 degrees, at least one of them. Now, once you've kind of finished this little section of the molecule, move over to nitrogen and analyze what's going on just around nitrogen. Once again, trigonal planar, but one of them is a lone pair. I'm going to make my lone pair one go down for the sake, since I'm running out of room down here. I'll make him go down, and I'll continue the molecule this way. Oh. And you just have to make sure that you label the angle. Now, which angle is less than 120? It's this one. It's this one, less than 120. And then you've kind of completed this section of the molecule. Now, this one here, oxygen, is going to be tetrahedral electron geometry. 2 of them are lone pairs, so I've got this one here. Let me go ahead and do the one that's up, this be a lone pair. I'm trying to draw that tripod camera tetrahedron. This one I'll make a lone pair, and then this one I'll make hydrogen. Okay, so that's that tetrahedron, and this is the angle that is less than 109.5 degrees. And that is a VSEPR model of this molecule. It gives you an idea of the shape. This is really important in organic chemistry and hugely important in biochemistry. The shapes of molecules and of sections of proteins and of sections of antibodies, which are a type of protein, the little edges of enzymes, that's the whole point of that lock and key substrate enzyme interaction. The shape is hugely important when it comes to higher levels of chemistry. All right, that's a VSEPR model. Let me put one more on the board as an example of a larger molecule that we can analyze. One of your homework questions, I believe, has a larger molecule. With that one, if you had in the homework question on homework 4, I think I wrote it on the explanation, but with the nitrogen, you have to add a lone pair. It's not written in the type of, you know what, let me just show you. It's not written in the type of drawing that they did, but you're supposed to essentially add it in. I think it's number 68 that I assigned, but anyhow. You basically have to complete the octets. So for instance, the oxygen, he really should have 2 lone pairs. That would give him an octet. This oxygen should have 2 lone pairs. So should this one. So should this one. The nitrogen, you can see he has 3 bonds. That means he really has a lone pair there. They're not showing it. They are showing the effect of it. They're showing where the other angles are because of the lone pair, but they're not showing it in there. So if it helps you to just write the 1 lone pair on nitrogen and 2 lone pairs on oxygen atoms, that might help you get the right answers. All right. Let's go back to one more example of these larger molecules. Let's try this molecule here. So here's the Lewis structure. Once again, it would have to be given. I wouldn't expect you to come up with this on your own. How this molecular formula would be written is C3H. Normally it would be written like C3H5OH. But like I said, that would not be your job to take that and draw a Lewis structure of it. You need to have a little bit more knowledge to be able to do that. But if you were given this, could you turn it into a VSEPR model? Go ahead and pause the video, see if you can do exactly what I did before, and I'll just work silently and put the answer on the board. In terms of what you write under each interior atom, you really need the number of electron groups. And then what you mostly need is the bond angles. The bond angles to really draw this. And maybe the molecular geometry. So I'm just going to write the electron groups, the number, the 2, 3, 4, 5, or 6, the bond angles, the molecular geometry, and I'm also going to write the hybridization. Even though you don't really need the hybridization, but we're getting into that soon, so I wanted to write that in there too. Okay, if you were watching me do that, I did pretty good with the artistry at the beginning. Okay, so I did a tetrahedron, and then, you know, when I was working on the second carbon, actually, this is not really that good at all. Where's my eraser? This really should be, I'm gonna make it a little bit more 120-degree angle. Look a little bit more like a Y. Okay, that's a little bit better. I fixed it a little bit. Then you get to here and it looks like a Y, but the biggest thing is that you label it 120, 120. Here, to draw the tetrahedron when you've got two lone pairs gets a little bit tricky, and obviously you can just do the best you can, but that's my attempt at the trigonal planar over here. But the most important thing is that you label the angle less than 109.5, and you can see that I did label the right angle. In other words, this angle is not less than 109.5. Neither is this one. Neither is this one. It's this one. That's less than 109.5. The one between the two bonding groups. Alrighty, so that's kind of helping you understand that you really just fixate on the interior atoms when the molecule is big. Because anytime you have an interior atom, it's like you have a joint, and the molecule will twist and turn to accommodate the electron groups. Alrighty. Moving on to our last theory, valence bond theory. Valence bond theory is, for us, the most advanced theory that we're going to be tackling. There is one that's even more advanced, and it is covered in chapter 10, called molecular orbital theory. For the sake of time, I never cover it in this class, but so I always just end on this one. It's kind of a nice one to end on. So valence bond theory, it's the most complex theory to analyze chemical bonds. And what valence bond theory does is it asks this question: which orbitals do the bonding atoms use to make covalent bonds? I'm going to reduce it just to covalent bonds. That's what we're going to be analyzing, covalent bonds only. So you can see that it's asking a different question than VSEPR modeling. VSEPR modeling was about the bond angles. This is all about, okay, I want to actually know which orbitals. And this takes us back to orbital diagrams, which is what we learned in chapter 8. And it really is saying, okay, you have an atom, it has electrons in orbitals. Which orbitals does it use to make bonds with other atoms? That's really the question. So let's go ahead and start with like the easiest, most simple molecule on the planet, probably, which is H2. H2. So hydrogen bound to another hydrogen. And let's literally look at this from the bottom floor, like the fundamental, simplest way of looking at this. You have two hydrogen atoms. So let's kind of set the table. Okay, so this is the molecule we're going to analyze. Let's talk about how this happened. How did this molecule happen? You had a single hydrogen atom, and you had another hydrogen atom. All right. Before you have a molecule, they were separate. All right. And so what's going on? I mean, we're looking at the electrons, because obviously the electrons being shared is how we know the bond happens. Okay. Actually, let's go ahead and back up just a second. Let's have that Lewis structure on the board. We've done that Lewis structure before, but the Lewis structure is simply just one single bond between two hydrogen atoms. All right, so the hydrogen atom, the first hydrogen atom has one electron, because that's how many electrons hydrogen has, and it lives in the 1s orbital. And by convention, we always make it spin up. Okay, that's hydrogen's orbital diagram. The other hydrogen has the same orbital diagram. All right, so when you do valence bond theory, or how do you apply it, what I do is I start with, it's not quite a step-by-step like the other ones, but I start with this. Set the table, meaning draw orbital diagrams for the atoms that are involved in the bond. So draw them just as two separate hydrogen atoms. Okay, and now here's the key point of valence bond theory. Okay, The key point of valence bond theory is a covalent bond occurs when two half-filled orbitals. Okay, a half-filled orbital will look like this, always. A half-filled orbital is just one electron in an orbital, because as you know, an orbital can contain 2 electrons max, so half-filled is 1. When 2 half-filled orbitals overlap in space, overlap in space literally means this one moves towards this one, the orbitals. Okay, I'm drawing them in the form of a box, but remember, they're s orbitals, they're spherical. When they overlap in space means they enter the same space of the universe. I'll show you a nice picture in just a minute. Overlap in space, allowing their electrons to spin pair. Okay, when an electron can spin pair with another, that means one of them gets to spin up and one of them spins down at the same time. That ends up lowering the energy of both atoms. Electrons like to have a partner to spin pair with. So allowing their electrons to spin pair, thus lowering the energy of both atoms. And remember, in the universe, matter wants to lower its energy. There's a driving force to chill, to get more stable. And so that's exactly what they do. Those 2 hydrogens, if they're entering the same place, the beaker, you put them together, they're going to approach each other. Those the orbitals will overlap, and the electrons will spin pair. And as a result, you will get the 2 electrons spin pairing in a single overlapping orbital. And so when we talk about valence bond theory, you literally are just understanding that. Actually, let me go ahead and draw this picture. This is the way of doing the boxes, okay? Let me draw this picture. Remember, if you have a hydrogen atom, you have 1 proton in your nucleus. I'm going to draw this a little bit more realistically. That electron is in 1s orbital. Here's the 1s orbital, the 1 electron. Here's the first hydrogen. When you have this bond occurring, it's because this hydrogen has come into the same space, this hydrogen, and you have his electron spin pairing with his electron in the same orbital. So what are they both using for this bond? These are both using 1s orbitals. And the way that we would describe that is to draw like hydrogen's 1s orbital is overlapping with the 1s orbital of the other hydrogen. If you look at on your textbook, let me show you. Actually, your textbook does it a little bit different, but it basically has a line right there. But it's just basically showing you, I'm just looking at the formulation on like page 459. You can see that they have the, well, actually this is hybrid orbital, so I won't go too far into that. But anyhow, they just have the hydrogen. They basically put the orbital as like a little subscript as to which orbital is being used. Now, you're not going to have to write that on my test, or else I would have been more clear about it. But you should know that the hydrogens are both using 1s orbitals, because that's what they came with. There's one graph, there's one figure that is a really nice figure, and let me talk about it real quick. It is figure 10.6 in your book. Don't minimize the helpfulness of figures. I used to do that as a student, and it was a mistake. It's very good to look at figures. Let's go ahead and talk about what's happening here, because this is what I'm trying to draw on the board, but it's prettier here. So you've got these 2 blue circles. That's 1 hydrogen atom with an electron in a 1s orbital. They don't show the electron because remember, we don't exactly know where it is. We just know it's in here somewhere. Here's the other hydrogen. He's got a 1s electron. Now, when they're far apart from each other, they're not bonding. And the red line is showing you the amount of energy of the atoms. Notice it's kind of high energy. It's high up on the y-axis because they're both very unstable. This situation is unstable for the atom. It doesn't like to have a half-filled orbital. As they start to move closer to each other, you can see that the orbitals are starting to overlap, okay, which is allowing those electrons to spin pair. And you can see that the energy of the atoms is going down. That's good. That means that that's what they want. That's why they form this molecule. This is the H2 molecule, by the way. At a certain point, the distance is perfect, and you get the lowest amount of energy for both atoms, and that's what you would call the bond length. The HH distance at that point is the bond length. That's really where they settle in the molecule. Hypothetically, if you were to push them closer together, that energy would shoot up because what would happen is their two nuclei would start to interact, and they both have protons. They don't want to be near each other. So there's like a perfect distance. So this is basically, from the point of valence bond theory, helping you think about the formation of a covalent bond from a different point of view. It's this concept of electrons trying to spin pair by overlapping their orbitals. All right, so that's all fine, well, and good, and hopefully you can see hydrogen uses 1s orbitals, and it's really not that complicated with hydrogen. It would be lovely if that's where it just stayed for all atoms. However, fairly quickly, we're going to realize that it's more complicated than that. All right, so let us get into analyzing the molecule that's going to kind of point out the problem here and what we have to do to fix our model. And we have to introduce this concept called hybridization. You've been hearing me talk about hybridization or hybrid orbitals. This is where it comes in. Let's go ahead and talk about the molecule CH4. Methane, okay? So we're going to use everything that we just put on the board with H2, but apply it to a slightly bigger molecule, CH4. Let's analyze this using valence bond theory, which is basically looking for what orbitals the molecule is going to use to make their bonds. Now, let's back up a minute. Remember, you can never just jump into valence bond theory. It rests on Lewis and VSEPR. Remember how I told you they come, like, start one to the next? So what you always do is you're going to start with a Lewis structure. Luckily, we've done this one many times. The Lewis structure of methane is just carbon to hydrogen, 4 single bonds. The VSEPR model. Carbon has 4 electron groups, making it have a tetrahedral electron geometry. With 109.5 bond angles. Okay. So with all of this in mind, all of this being accepted as true, okay, and by the way, this molecule is perfectly symmetrical because all of those angles are exactly the same. And it's nonpolar because carbon to hydrogen bonds are nonpolar. Now let's kind of look at what orbitals is it using. Are they using s orbitals, p orbitals? Like what kind of orbitals is this carbon atom using to make the bonds with hydrogen? So let's set the table. So this is what I'm saying. When you use valence bond theory, you kind of set the table and you just look and see what the atoms, where their electrons are. Those are the orbitals that they're going to use, presumably. So hydrogen's got his 1 electron in the 1s orbital. And the hydrogens are ready to form the bonds, because to be able to form a bond, what you need to provide your end of the deal is a half-filled orbital. Hydrogen comes ready to go. It's got half-filled orbitals, so if it can just kind of enter that space with carbon, it's ready to go. It's going to play its role properly. Let's look at carbon. Carbon. Let's draw an orbital diagram for carbon. Now, be very careful. When you're doing Lewis structures, you fixate on valence electrons. So carbon, you would always pick 4 because carbon has 4 valence electrons. When you draw orbital diagrams, it starts with 1s. You include the core electrons. So you have to go back to total electrons. So carbon has 6 electrons, and if you want to just quickly draw a electron configuration to make sure you don't forget it, it's 1s2, 2s2, 2p2. So that's carbon's electron configuration, but we need an orbital diagram, so let's go ahead and draw it. 1s2, 2s2, 2p2. And according to Hund's rule, they would fill up singly before they double up. Alrighty, so here's the issue that comes up from the scientist's point of view, trying to use this theory to understand real molecules. I'll frame this how it was explained to me, because I think it's exactly how scientists think about it. Problems arise with the theory when we consider this molecule. There's something that doesn't make sense, and when something doesn't make sense, we have to adjust the theory. That's exactly what hybridization is. It's the adjustment of a theory. So let's kind of go ahead and talk about the problems here. Let's be real explicit. The hydrogens are ready to form single bonds. As I said before, hydrogen's ready to go. But what you will notice is that carbon is not ready to form 4 bonds. We know that it does. Based on Lewis theory, VSEPR theory, we know that it forms 4 bonds. But where? Because understand, to form a bond, each atom has to contribute a half-filled orbital. Right now, carbon appears to only be ready to form 2 bonds. You can't form a bond in our understanding of valence bond theory with an empty orbital. It doesn't work like that. Or a full orbital. It doesn't work like that. It's got to be half-filled. So right now, it seems that carbon is not prepared, and it's not to form 4 bonds. That's not the only problem, though. There's a second problem, and that is, even if it was ready, even if we did have, for instance, 4 p orbitals, I mean, that can't exist, but even if it could, even if it was, p orbitals are at 90 degrees to each other. Remember, I mean, we don't usually label it, but this is the one on the x-axis, this is the one on the y-axis, and this is the one on the z-axis. So even with the 2 that are ready to go, the carbon would have to form 1 bond using a p orbital that's here, and another one using a p orbital that's on a y-axis. So this would be the x one, this would be the y one, and the hydrogens would come in. It would give you 90-degree bond angles, and we know that we don't have 90-degree bond angles. In reality, we have 109.5-degree bond angles. So this current carbon orbital diagram must not be what the carbon atom uses to form this molecule. Because of these problems, it doesn't work. So here is the way that this works. We have a fix to the theory, and it's a theory. It's not even fully true. We just use it because it helps us explain things that we see. People have recognized that it has a theory, it has holes in it. But scientists have kind of proposed this concept to fix the theory. And the fix is called, let me give you the title, hybridization of orbitals. That's the fix, hybridization of orbitals. And let me give it a sentence to explain it. In an atom, electrons occupy standard orbitals. And when we say standard, we're talking about Schrodinger's, S, P, D, and F. When you just have a plain atom, they live in standard orbitals, period. They're going to be in S, they're going to be in P, they're going to be in D, they're going to be in F. Nothing else. That's what happens if it's just an atom. However, let me go ahead and get myself some space because this sentence is a little bit longer. Once the atom enters a conglomeration called a molecule, in a molecule, the electrons can occupy either standard orbitals, those are still an option if they work for the atom, or you have a new option now, a new hybridized, or let me just say hybrid, new hybrid orbitals. And the hybrid, remember the word hybrid, even we use this for the concept of resonance hybrid. Hybrid means mixture or mixing of orbitals. The orbitals mix together. They do a remix together, and they use those new mix for their bonds. So let me go ahead and just, I'm going to explain what it's called in just a second. But this type of orbitals are not the ones that carbon's going to use for his bonding. They can't. It can't. It doesn't make any sense with what we know with data. So we propose that it uses a new mixture of orbitals. Let me go ahead and explain what I mean by a mixture. These new hybrid orbitals. It's very conceptual. And if you have a good imagination, you should be able to be okay with it. Some people struggle with this, but you just have to kind of allow yourself to, scientists do use their imagination a lot, to kind of understand things. It's informed imagination, but it is an imagination. Okay, so coming back to this here. Do you remember when I told you with VSEPR modeling, we had a last column and it was called hybridization? The issue here is that from the VSEPR modeling, when we got that it was 4 electron groups, and we kind of put them according to the table, we also immediately connected that to the type of hybridization. You don't have to come up with your own ideas of, oh, what kind of mix would it be? That's not your responsibility or mine. It comes literally actually from the Lewis structure. You count the number of electron groups, 4, and from that you know the angles, the electron geometry, and you know the hybridization. For this molecule, it uses sp3 hybridization. What in the world does that mean? Okay, and this one takes the longest to explain. I don't go through all of them, but this one takes the longest. sp3 hybridization. Come over here with me for a minute. What I always have students do is draw a rectangle, because it's going to help you visualize this. Draw a rectangle around the valence shell of the atom, the central atom, carbon. Okay, we're going to fixate, only the central atom's going to hybridize. These guys are not going to hybridize. Only the central atom will hybridize. Okay, so draw a valence shell around, or a rectangle around his valence shell. The reason is, remember, valence electrons are the ones that are involved in bonding. So these are the ones that are in play for the bond. This is a core electron. He stays on the carbon's nucleus and is totally uninvolved. So always draw a rectangle around the valence shell. And when we say that this carbon undergoes, let me write the word undergoes. He undergoes sp3 hybridization. And he does. We know that from the VSEPR model. What does that mean? What is to undergo? It's like a rework, okay? A nice analogy, I think, is to think of it like a blender. A blender mixes things together. When you undergo what's called sp3 hybridization, you throw into your blender an s orbital and 3, that's what the 3 means, 3 p orbitals. The atom itself throws them into a blender, obviously, the analogy, mixes them up, and what comes out are, if you put 4, okay, this is an important thing. If you put 4 orbitals into your blender, you will always get 4 orbitals out. But what comes out is not the same as what came in because they got all mixed together. The 4 orbitals that come out are called sp3 hybrids. You get 4 of them that come out of your blender. They are a new type of orbital. They don't look like S's. Remember, S's look like this, circles or spheres. They don't look like P's. Remember, P's look like those, you know, two lobes and a node. They don't look like these anymore. The sp3 hybrids, they kind of almost look like bowling pins. That's what one of them looks like. It's a new type of orbital. And you get 4 of them. And remember, just like p orbitals have like the 90-degree orientations, the sp3 hybrids, there are 4 of them, will be oriented to each other like in a tetrahedron. Let me see if I can draw this. Like that. In your book, you'll get a better picture. Let me see if I can show you. Yeah. This is better. An s orbital and 3 p orbitals get mixed together, thrown into your blender, and after the process comes out, you get these 4 independent hybrid orbitals oriented to each other in this tetrahedron, just like VSEPR modeling would predict. Okay, so new shapes. Now, the key here is that all of these are equivalent in terms of the energy. All right, so let me go ahead and show you how to kind of think about this here. After hybridization, this s orbital and all 3 p orbitals get mixed together into your blender, and out come these new hybrid orbitals. Now, I always draw the hybrid orbitals like lines, not boxes, just to represent that they're kind of a new mixture of orbitals. These are all called sp3 orbitals. Now, when we go to, and you know what, let's redraw our core electrons. Don't forget that these are still there. They're not going to be involved in bonding, but they're still there. Now, how do the electrons of carbon fill up these orbitals? Because it's like a new type of orbital diagram. You still have these 4 valence electrons, but here's the difference. When you had standard orbitals, this had to fill up first before you could start entering these, because the 2s was lower in energy than the 2p, off-ball principle. These had to fill up before you could enter this. But when after hybridization occurs, these are all, the word is called degenerate. Put that in your notes. Degenerate. Degenerate just means equal in energy. Equal in energy. And that might not seem like a big deal, but what that means is that it follows Hund's rule. Those 4 electrons will fill up one at a time. Because they're equal in energy, they will follow Hund's rule. That's huge, because now you can see that after hybridization, our problem has been fixed. Hydrogen is ready to form these bonds, and now so is carbon. This hydrogen would come in and overlap with this guy. This would come in and overlap with this guy. He would, 3rd hydrogen comes in here, 4th hydrogen comes in there. And you now have 4 single bonds, and they are oriented to each other at 109.5 degree angles. Well, they don't have that molecule in your book, so I can't show you this. Oh, yes, they do. There it is right there. Carbons, hybridized orbitals, now in purple. Hydrogens, 1s orbitals being used for the bond. And so that is, if someone was to ask you what orbitals are being used for the bonds, like for instance this bond here, carbon is using an sp3 orbital, and hydrogen is using its 1s orbital. That's how you would describe that. Carbon is using the sp3 orbital, and hydrogen is using the 1s, and that's true for all of those bonds right there. All right, so you can see that hybridization fixes the model, and that's what it means that carbon undergoes sp3 hybridization. Now, sp3 was only one of the types of hybridization. There were 4 others. What I just want to do is I just want to talk about one more, because, you know, for the sake of time, we got to kind of have an end somewhere here. I want to talk about sp2 hybridization, because once you get that, it allows you to understand the significance of sigma versus pi bonds, which is really kind of like the last topic that we have to cover to make sure we understand this. These are topics that get reused in later levels of chemistry, so that's why it's kind of important to hit it now. And you don't really hit it in Chem 102. This is like the time. All right, so that was an explanation of sp3 hybridization. sp2 hybridization. It won't take me as long because we're going to reuse the same concepts, okay? Once you get it, you kind of keep applying it a little bit differently. All right, so to explain this, we need a molecule that actually uses this. I'm going to use the molecule C2H4. Let's start with the Lewis structure, so see what we can get from Lewis theory. It takes us so far. If you were to draw the Lewis structure for C2H4, I think I've said this before, but anytime you have multiple carbons, connect them together. And hydrogen always has to be hanging off the edge of the molecule because it can't form two bonds. So that would help you figure out how to organize your atoms. And if you did your steps, you would get this Lewis structure. That's the Lewis structure. You can see this molecule is one of these ones that has multiple interior atoms. So we actually have to analyze both carbons because you'll have kind of geometry around him and you'll also have geometry around him. So let's get the kind of the magic numbers. The magic numbers for both of these are 3. Magic numbers meaning the number of electron groups. Remembering that double bonds only count as 1 as far as VSEPR theory goes. From that 3, we're going to get the angle, 120. We're going to get the shape, trigonal planar, both of them. And we're going to get the hybridization, sp2. Remember, we know that from the chart that we built in the last video. Anytime you have 3 electron groups in your Lewis theory, sp2 is the hybridization that the atoms will undergo to accomplish that. Let's go ahead and draw our VSEPR model, because it sure helps to kind of unite these theories together and see it kind of holistically. So carbon, I'm going to draw this one there and this one up here. And these are 120-degree angles. 120, 120. And that's our VSEPR model. All right, so now let's come at it from our newest theory, valence bond theory. Valence bond theory. Valence bond theory, just think, I need to set the table with all the atoms' orbital diagrams individually. Every atom that's in that molecule, I'm going to lay on the board as if it was just a single atom. So let me start with the hydrogens and just get them out of the way. So you've got 4 hydrogens. Hydrogen will always look the same. And hydrogen doesn't undergo hybridization. There's nothing to hybridize, it's just one orbital anyways. And it's ready to bond. Okay, for the sake of my board, I'm going to have to erase some of this. You've got it hopefully in your notes, but I'm going to need this space. But we can see that what the molecules is going to end up looking like. Now, let's go ahead and lay out the carbons. Now, I just erased the Lewis structure, but there were 2 carbons. I'm going to label them carbon 1 on the left and carbon 2 on the right. So here's carbon 1. Let's go ahead and draw, actually, you know what? Let me leave even a little bit more room. Let's draw his orbital diagram. And by the way, the only atom that I would ever ask a student to kind of draw the before and after hybridization will always just be carbon, because carbon is so fundamentally important to chemistry. So there's a reason I keep choosing carbon, because I want you to see what happens to carbon before and after he hybridizes. And as you'll remember, this is still the orbital diagram of carbon. Let's draw the second one. This is before any kind of hybridization occurs. This is before the molecule forms. Okay, so we got 2 carbons. Now let's do our box around the valence shell, the orbitals containing valence electrons, because we want to make sure, this is the deal, you don't want to hybridize your core orbitals. They don't hybridize. Only your valence orbitals hybridize. So be careful. That's why I actually have you draw this to enclose the ones that we're fixated on. So we know from the Lewis structure, actually, I guess, or from the valence bond, from the VSEPR modeling, that it undergoes sp2. We know that because that's the, 3 trigonal planar. All of that leads us to sp2, as does this one. So what does it mean to undergo sp2 hybridization? Well, come back to your blender for a minute. sp2 means you mix together an s orbital. And by the way, remember, or be careful, a lot of times students, they misunderstand. They think we're mixing electrons together. We're not mixing electrons. We are mixing orbitals. Think of the boxes. Don't worry about the arrows. Not yet. It's the orbitals that we're mixing together, the boxes. I mean, they're not boxes, as you know. They're zones that the electrons can live in. But when you draw it like this, you think of the boxes. sp2 means we're mixing together an S, and how many P's? This time, only 2 of them. Only 2 P's will get mixed together. Okay? Now, how many did I throw into the blender? 3. 3 in, 3 out. The blender will not invent or lose orbitals. You will get the same number that went in as come out. What comes out are 3 what are called sp2 hybrids. sp2 hybrids or sp2 hybrid orbitals. They are all degenerate. If you don't remember what degenerate means, look it back in your notes. They are all degenerate. So coming back to here, which ones did I mix together? I mixed together the S box, and this time only 2 of the P's. 2 of the P's. 3 went into my blender, so I'm going to get 3 of these sp2 hybrids to come out. Keep your core electron there. You didn't, or your core orbitals there, core orbital with the 2 electrons there. These 3 got mixed together, and you got 3 that came out that are like Huey, Dewey, and Louie, all the same. Who didn't get mixed? This is the big thing. That last 2p orbital, that standard orbital, never got mixed together. He still exists. He didn't get thrown into your blender. Now, let's fill in now that we have our orbitals in place, fill in your electrons. How many were there? How many valence electrons are there? 4. Now, remember, these are all degenerate, so they follow Hund's rule. However, the sp2, because you mix together S's and P's, they're kind of higher in energy than a normal S, and they're so close in energy to the 2p that that last electron doesn't have to recycle back here. They will all fill up singly. These are close enough in energy that they follow Hund's rule, even though technically this one is slightly higher in energy than these. It's close enough that they fill in singly. Okay. So now you've got your carbon 1. Let's see what carbon 2, well, he'll do the exact same thing, because we know from our earlier discussions that he also undergoes sp2 hybridization. And he will look the exact same way. All right, now time for us to analyze these bonds. What kind of orbitals are being used for all these bonds? Well, let me come back and see. I need a little bit of space here. Let me lose this part here. Let me just have the carbon what it now is, not what it used to be. Because this is what it is after it hybridizes, and that's kind of where we are in time now. Both carbons have hybridized. That's carbon 1, that's carbon 2. Let's look at that molecule. I am going to draw the molecule a little bit more accurately here. Okay, let me have carbon 1 right here. Carbon 1, that molecule has, we're going to leave out the core. Core electrons are not involved in bonding, just ignore them. They exist, but ignore them. Carbon 1 has 3 sp2 hybrids. hybrid orbitals. As you might guess, sp2 hybrids are an S and two Ps. You get these new bowling ball shapes. They're all equivalent in size and energy. They will orient to each other in this 120-degree angle shape, which we call trigonal planar. So if I were to draw those orbitals, I would draw them in a 120-degree shape. These are sp2 hybrids. Okay, so I've just drawn him, him, and him. Alrighty, let's kind of take care of a few of our bonds here. This hydrogen here, this guy here, is going to overlap with one of our sp2 hybrids, and we'll get our very first bond, hydrogen. Now he will use a 1s orbital. They will both contribute a single electron. He'll contribute this one. This carbon will contribute this one. They'll overlap. I have two little dots drawn in the overlap there. And that will create your first single bond, because that's what a single bond is. Remember when we started with H2, the overlapping, the electrons get to spin pair, it lowers the energy, and you have a bond. This hydrogen right here, we'll do the same over here. That will be our second bond in our molecule. So if we were to talk about this bond, hydrogen will use the 1s, and carbon will use the sp2. Alrighty, now let's go ahead and, we've dealt with these guys. Let's go ahead and talk about what happens right here. Okay, this carbon, this one here, sp2, is now going to interact with, actually, you know what? Let me deal with the other carbon first. Let me do it carbon 2 first. Let me deal with the hydrogens first. This carbon 2 is going to also have three sp2 hybrids. 1, 2, 3. Notice I overlapped these two. I'll come back to that one in just a second. Okay, these are sp2 hybrids. sp2 hybrids. Let's deal with the two hydrogens. This one here will come in and overlap with carbon 2's, one of his. That is this one. This is hydrogen. This is the 1s orbital. Kind of the exact same thing that the other one did on the other side. This hydrogen will overlap here, down here. You can see we're essentially very succinctly analyzing the whole molecule from the point of view of what orbitals it's using. That's a valence bond theory. So we've dealt with these two. We've dealt with these two carbon hybrid orbitals. Now, look what happens here. Carbon 1's sp2 hybrid will end up overlapping with carbon 2's sp2 hybrid right here. Carbon 1 will contribute an electron. I'm going to make it a dot. Carbon 2 will contribute an electron. I'm going to make it a dot. And voila, you have your first bond between the two carbons. Let me come back to our simple VSEPR model. We've explained this bond and this bond, this one and this one, and we just explained the first of your carbon-carbon bonds. That's this one. Now, here's the big kind of where it all wraps up. The last bond, this one, is fundamentally different than the previous one. The first carbon-to-carbon bond uses these hybrid orbitals, sp2 to sp2. The second one uses standard 2p orbitals. Okay, now here's the deal. A 2p orbital looks like a 2p orbital. 2p orbitals look like this. So let's draw them in. And they both have a single electron in them. All right. Now, what happens is these two carbons, their 2p orbitals will overlap. They'll kind of do this deal. They'll overlap. There is an overlap And there is a bond that happens here, just as there is a bond that happens here. However, the type of overlap is different because it's not a end-to-end overlap like the sp2s, but it's a side-to-side overlap like the P's undergo. And so this is the difference between what we call sigma bonds and pi bonds. What we call a sigma bond is this black line, sigma. Sigma bonds, and by the way, it's a Greek letter. It's like a 0 or like an O with like a little tail sticking off the top, like a hat. Sigma bonds result from what we call end-to-end overlap of orbitals. End-to-end overlap of orbitals. And literally you can see that this was a sigma bond because of the way they overlapped. If it's here's the thing, if it was a hybrid orbital, it's sigma. Anything that is a hybrid orbital is a sigma, but you can see it better here. End to end. What about this one? See how they're overlapping end to end? Sigma, 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 sigma. All of those are sigma bonds, okay? The only time you're going to see a pi bond is when it involves the overlap of p orbitals. This one in red, this line here, are called pi bonds, pi, and like the math pi bonds. And these are side-to-side overlaps of orbitals. This is a pi bond, this top one, because it involved p orbitals that overlap like this. Now, use your common sense. Which one do you think is stronger and which one do you think is weaker? Which one looks like a better overlap? Hopefully you see like me. Sigma bonds are stronger. They overlap like this, whereas pi bonds are weaker. That's significant because when you enter organic chemistry, if there's a double bond that's going to be broken, he would get broken first. He's the weaker of the two bonds. And it does end up coming into like higher levels of chemistry. Pi bonds would be broken first. Now, usually at this point, students are freaking out because it looks hard. And if it's the first time you ever saw it, I get it. It does look hard, even though it should look concise. It is logical, very, very logical. Concise, yes, but challenging to get for the first time. I get that. Here's the beauty of it, though. When you have a Lewis structure, or like a VSEPR model, just wherever you've got bonds and stuff like that, to discriminate sigma versus pi bonds is wildly easy. Let me go ahead and get myself a little bit of room here. You can almost draw yourself like a little legend, like a little key. In any Lewis structure, single bonds are always sigma bonds. Double bonds always have one sigma and one pi, just like we saw with this double bond. Okay, I didn't finish labeling this. These were the 5 sigmas. That was a sigma and this was a pi. You can do these in either order, it doesn't matter. A double bond will always have one sigma and one pi. A triple bond will always have one sigma and 2 pi bonds. And so this is going to be always true, okay? So let me go ahead and make sure that you can see how easy this is. If I had a question that looked like this, I believe the Lewis structure for cyanide is this. I'm just trying to think of something that has a triple bond. Carbon would have 4 valence electrons. Nitrogen would have 5. 1 extra gets you 10 total, 5 pairs. 1, 2, 3, 4, 5. Every atom has an octet. Yeah. If I was to give you this Lewis structure and I said, how many sigma bonds does it have? How many pi bonds does it have? You literally can apply this key. It has 1 sigma and 2 pi's. You don't have to draw all this valence bond theory. You do not need to recycle all of this. Understanding valence bond theory is about understanding it, not really about being to explain it like I just explained it. That took years to actually get kind of that good at it. But you want to, that sounded braggy, but you know what I mean. You want to try to understand certain fundamentals of it. It's not like you have to draw all this out every single time. Another example, if I was to ask you how many sigma bonds and how many pi bonds does carbon dioxide have? The way that you would do that is you would draw a Lewis structure. The Lewis structure for carbon dioxide is this. From the Lewis structure, you didn't know how to do this before, but now you do. From the Lewis structure, you can label sigma and pi bonds. Double always has one sigma and one pi. So the answer would be it has 2 sigma bonds and 2 pi bonds, period. Now, the last thing I'd like to say is why. Why in a triple bond is there 1 sigma and 2 pi's? Let me go ahead and see if I can explain this. Let me think here for a second. I don't want to use that one. When you, let me think. Let me use carbon dioxide, because this will not present any kind of added problems here. Carbon dioxide is a very familiar molecule, so let me use him to explain. Even though it's not really addressing the triple bond thing, it'll still work for what I'm trying to teach here. How many electron groups does he have? He has 2. 2 electron groups, which tells us everything. It tells us that he has 180-degree angles, that he's linear, and that he uses what's called sp hybridization. sp hybridization, okay? Without going into the whole thing before, let me just do a tiny bit on it. Carbon, I'm not going to do the whole molecule. It will take too long, and I want to be done too. Carbon has, as we know, this orbital diagram. Just keep kind of saying kind of the same thing over and over again. Before it hybridizes, it always looks the same. Let me draw the valence. If we know that it undergoes sp, which we know because of the 2 electron group linear geometry, because that's what's in the chart. So sp means it hybridizes an s and a p, which means that in the blender go an s and a p, 2 in, 2 out. So as a result of sp hybridization, you will only get 2 sp hybrids. What you have that didn't get hybridized were 2 2p orbitals. And as we discussed before, the carbon, these will be able to form sigma bonds. Hybrid orbitals will always form sigma bonds. P orbitals will form pi bonds. So when you have sp hybridization, that's the only time that you're going to be able to form 2 pi bonds, because that's the only time that you'll have 2 2p unhybridized orbitals. So you can see that that's exactly what we see with carbon dioxide. It kind of links this concept of sp hybridization to the formation of 2 pi bonds. So you either are going to have, like the carbon here, you're either going to have 2 double bonds, which will get you the 2 pi bonds, or you'll have a triple bond. And at the moment, I couldn't think of something, although you know what, this would have been perfect. I could have used that molecule. You'll either have your 2 pi bonds come in the form of 2 doubles, or a single and a triple. But either way, both of them use sp hybridization, because sp hybridization is the only one that will allow you to form 2 pi bonds. That part was maybe a little bit more confusing than I had intended, but hopefully it helped. You can at least see with sp hybridization, you're going to get mixing of an s and a p. You'll only get 2 hybrid orbitals out of that, leaving you the 2 that didn't hybridize to form pi bonds. sp3d just means you also mix together a d orbital. sp3d2 is just that you mix into your blender 2 d orbitals in addition to your s and 3 p's. And when you have 6 in, you get 6 out. So you'll always get 6 sp3d2 orbitals. That would be like what sulfur would have used for SF6, octahedral, that type of electron geometry. That is the end, really where I end every single Chem 101 course, talking about sigma and pi bonds, how to tell just by this key, like what type of bond you have, how to really see with your own eyes what a sigma bond is versus a pi bond, why they're stronger where these are weaker, why sp3 hybridization doesn't give you any pi bonds, sp2 hybridization gives you 1 pi bond, and sp hybridization will always give you 2. You'll see that if you dig into your Lewis structures, it's very satisfying because you just pick any Lewis structure, it will kind of obey these concepts, okay? And it all is like a complete story if you allow yourself to dig into it. Hopefully it makes sense to you. Use the textbook as well. These pictures that the textbook do are, you know, much better than what I'm drawing on the board, but sometimes hearing it from someone's mouth can also kind of help you to understand what you're reading as well. On the exam, I still haven't figured out exactly what type of format I'm going to use for the final exam. I'm going to make it very fair, but I'm also going to make it a test of whether you have learned this material. I want to assure you that you will not have to do valence bond theory where you are drawing arrows and like I was doing, you know, this hydrogen to this carbon and all that stuff like that. I will be able to tell whether you learned it and understood it based on the questions that I ask. Any kind of new vocabulary words could show up. This type of thing could show up. You should know, you know, how many sp3 hybrids you'll get when you have them. The answer is 4, because 4 in, 4 out. You should know that the hybridization is connected to the number of electron groups in your Lewis theory, so it goes Lewis to VSEPR to valence bond, that kind of thing. I will write a very fair final exam, but it will test your understanding, and it will not be the type of thing that you can just Google, because that's pointless. It doesn't really test anything. So, all right, good luck with your last section. Hopefully you at least a little bit enjoyed it. I enjoy it because I think it's very logical, and I like logical things. So anyways, have a good rest of your day and good luck.